All right, here we are focusing on radians again. In section 3.2, we're going to talk about applications of radian measure. Now, we already introduced the concept of the arc length on a circle. In our last section, we talked about the fact that 1 radian is when the angle of the size where the radius of the circle is the same, whoops, there we go, where the radius of the circle is the same as the arc length of the circle, because that value of theta in radians is S over R. Arc length subtended by the angle over the radius of the circle. When these two things are the same, theta has a measure of 1 radian. Now, rearranging the the three terms in this formula give us how to find the arc length on the circle. This arc length S would be the same as R times theta. If I multiplied both sides of my equation by that denominator R, well, it's going to cancel out over here, and I'm left with S equals R theta. This is true as long as theta is in radians. When I apply this formula, the value of theta must be expressed in radians, not degrees. It doesn't work for us when we are working in degrees. So make sure that you keep track of that when I'm finding these values, when I'm using these area formulas and these arc length formulas, that you have to have theta in radians. Okay, for example, a circle has a radius of 25.6 centimeters. Notice that I have 25.60, so that implies that we're going to be keeping 4 significant digits with our answer. Find the length of the arc intercepted by a central angle having each of the following measures. Well, 7 pi eighths, 8 pi eighths is pi. 7 pi eighths is almost all the way around to pi. So if I'm looking at a circle and I've got an angle theta that is 7 pi eighths, I am almost all the way around. It's not going to be pi, but it's going to be close. Well, I'm going to use my formula S equals R theta. S equals R theta. I am on a roll today. You guys, I do this in the classroom too. Thankfully, I caught myself there. I need someone here to help me catch it. S equals R theta is my equation. I'm solving for S. I'm finding that arc length. My radius is given as 25.60. My angle theta is 7 pi eighths. And it's already in radians, so I don't need to do anything to change that. I'm just going to plug that into my calculator, which has gotten shifted all the way across the table. I'm going to plug that into my calculator. I've got 25.6 times 7 pi, and then divided by 8. And I've got 70.37, because remember we're keeping 4 significant digits, 70.37, and we are in centimeters. So that is the length of the arc that is subtended by that 7 pi eighths angle. That's the value S. Okay, let's look at the next one. We're given an angle of 54 degrees. Well, I know that 54 degrees is, here, not quite 60 degrees. This is my angle theta, 54 degrees. I need this arc length S. I'm still on the same circle with that radius of 25.6. I'm given that radius hasn't changed. Theta is 54 degrees, but this isn't going to work for me with theta in degrees. So I'm going to need to say, you know what, that is 54 degrees. I need to divide out the degrees. So I'm going to multiply in that pi 80ths. Those degrees cancel out, and I have changed my angle from degrees to radians. The degrees are going to cancel out here. So to find the length of that arc, I'm going to multiply my radius, 25.6, times 54 pi, and divide it by 180 to make sure that I get my answer in, what did I just did something did not work out. the way I wanted it to work out. Let's try that again. 24.6 times 54 pi divided by 180. There we go. I hit a wrong button somewhere. There's no way it was that big. So my, because, and here's why we're in quadrant 1, so I know that since my angle is less than 1 radian, I know that this is going to be less than the radius, the length of S is going to be less than the radius of my circle. Alright, so I need to round that to 4 significant digits. That gets me an arc length of 24 and 13/100ths of a centimeter. Alright, we have 2 more examples. The same type problem. For these examples though, we have a new circle with a new radius. Now our radius is 18.2 centimeters. We're still keeping 4 significant digits, notice. I haven't had to use my calculator, worry about whether it's in degree or radians, because I'm not using my function, my trig function buttons. That whether I'm in degrees or radians only matters when I'm using these functions calculations. If I'm using sine, sine inverse, cosine, cosine inverse, tangent, tangent inverse, I gotta be in the right mode, degree or radian mode. If I'm just doing multiplication and division, the mode doesn't matter because I'm not informing the trig functions on that calculator. Okay, so pause the video. Make sure you know how to set these up. I'm just going to give you the answer so that you can check. Alright, this is what you should get when you are using your formula S equals R theta, remembering that for this one I'm given degrees, it has to be in radians for my formula to work. Okay, another application problem here, finding the distance between 2 cities. Latitude gives the measure of a central angle with the vertex at the Earth center whose initial side goes through the equator and whose terminal side goes through the given location. So if you think about what you learned in geography, latitude and longitude are measures of location. If we are doing latitude, we've got the pole, north-south pole on the Earth. Measures of latitude go around horizontal with the equator. Those are our latitude. Longitudes go up and down vertically. Latitude, I couldn't keep this straight in elementary school, so latitude is fatitude. It's the distance around. But those are my latitude, lines of latitude are horizontal and they're parallel to the equator. It tells us how far above or below the equator something is. So let's just dive into this. Erie, Pennsylvania is approximately due north of Columbia, South Carolina. Now, due north, yes, but it's on the surface of the Earth, right? So it's on a curved surface. We've got Erie, Pennsylvania is due north of Columbia, South Carolina. So here's Erie, and here's Columbia. The latitude of Erie is 42 degrees north. So this angle formed from the equator is 42 degrees that goes to Erie. And the latitude of Columbia is 34 degrees north. So when I connect this line from the center of the Earth out, I get an angle of 34 degrees north. The radius of the Earth is going to be approximately 6,400 kilometers. And we want to find the north-south distance between the 2 cities. So this value S is what we're looking for, this distance S. I was given 2 angle measures, but neither of the angle measures is the angle theta that I'm interested in here. Do you notice that? Neither of those angle measures is the angle that I'm actually interested in. This angle theta, this central angle that's formed between Erie, the center, and Columbia, theta here is the difference between those 2 angles. So if I do 42 minus 34, I figure out that that angle theta is 8 degrees. Well, S this distance is equal to r times theta, and we're using the radius of the Earth as 6,400 kilometers. And then we've got theta. Well, theta is 8 degrees, but we can't use this formula in degrees. So we have to multiply in our radians and divide out our degrees to make it work correctly and give us the correct value. Now you can simplify here if you want to. That's fine, that's awesome, but you don't have to. You can just plug this all into your calculator. You should end up with about 890 kilometers. Now, how did I round to 890? Let's go ahead and let's plug that in and take a look at it. 6,400 times 8 pi, and then I'm going to divide that out by 180, and I get 893.6, which seems like the answer I would give, right? But that would be 4 significant digits, and when I look back at my problem, I've rounded the radius of the Earth to 2 significant digits, so I need to give my answer with 2 significant digits. My answer can't be any more specific than the least specific measure in the problem. Alright, let's look at the next one. Another application problem. We are winding a rope around a drum with a radius. Now the radius of our drum is 0.327 meters. Now we keep things pretty simple for our trig class because, you know, as we wind this rope around the drum, if we do angles of rotation, this radius is increasing with each rotation because we are winding rope around the drum, and so it increases the thickness, right? Like a pulley. You see the pulleys on the front of Jeeps, or, well, we're just going to stop there. But that rope winds around and increases the thickness. We are not winding more than 1 full revolution. In fact, we're winding less than a revolution. We are winding through an angle of 132.6 degrees, and we want to know this arc length. How much rope has been wound around the drum? So we've got our radius, we've got our angle. So we set up our function, s equals r theta, where our radius is 0.327. Our angle is given in degrees, so we have to make that adjustment, use our conversion factor to change it to radians. We divide out the degrees, we multiply in pi to get it into radians. And we are going to be keeping 4 significant digits. We're going to be keeping 4 significant digits if you count that 0 in front as a significant digit, right? So S, when you plug all this into your calculator, you should end up with 0.757 meters. Okay. I'm going to make the assumption that you guys know how to use your calculators by this point. We're going to move on to this gear problem. 2 gears are adjusted so that the smaller gear drives the larger gear. So when I turn this smaller gear, say clockwise, it's going to turn that larger gear about counterclockwise, and they turn together. Now this smaller gear drives the larger one, but because it's smaller, it will have to go through more than one turn to get back to the place. If this is the tooth that I start with, this is more than one turn of my smaller gear to equal one turn of the larger gear, right? So that's going to include some extra calculations. We want to know if the smaller gear rotates through an angle of 150 degrees, how many degrees will the larger gear rotate through? Well, they're matching up tooth by tooth. So the arcs are going to be the same. So the arc on the smaller gear is going to be the same as the arc on the larger gear. Now, something that you need to remember is not to round until the end, because when we have a multi-step problem, if you round in the middle, you've changed your answer potentially, depending on how many significant digits you keep. Okay, so we've got this smaller gear, S equals r theta, and for the smaller gear, R is 3.6, and theta is given as 150 degrees. The smaller gear rotates through an angle of 150 degrees. So 150 pi over 180, because we have to change from degrees to radians. Now my larger gear, S is also equal to r theta, and if S turns 150 degrees, how many degrees is that going to turn so that these arcs where the teeth touch are going to match? Well, we know that this radius is 5.4, but this value of theta, this is what we're after. This is what we're trying to figure out. This is also equal to S. That arc length is the same. The distance that rotates here is the same. Since S is equal to itself, I can say that right here, 3.6 times 150 pi over 180 is equal to 5.4 theta, and I can solve for theta. Now, how am I going to finish solving this for theta? Well, I'm going to need to figure this out, and then I'm going to need to divide whatever I get by 5.4. So let's see what happens as we go through and do this. Let's start with the information we got from the smaller gear. We have a radius of 3.6. Whoops, there we go. We have a radius of 3.6 multiplied by 150 pi, and then we divide that out by 180. I am not going to round that off. I'm not going to round. I'm going to leave it there, and I'm going to divide it by 5.4, the radius of the other gear. That's what I end up with. 1.745, etc. This is the right answer for theta, but this is theta in radians, because we worked with our problem in radians. When we get this value for theta, we get that value in radians. So it's 1.745, etc. My problem asks how many degrees will the larger gear rotate through. So I need to change this value in theta in radians to degrees. Alright, when I started in degrees, I multiplied by the conversion factor pi over 180 to end up in radians. Now that I'm in radians, I need to flip that so that I'm back into degrees. Now notice, I haven't rounded yet. This is still in my calculator. I wrote it down, kind of rounded off, but this is still in my calculator. So I'm going to use my conversion factor to convert back to degrees. I'm going to take my angle in radians, multiply by 180, divide by pi, and there is my angle theta in degrees. It rotates through a 100-degree angle. Does that make sense? Well, yeah. This is smaller, so the angle that it turns through is going to be more than this larger gear has to turn through. Okay. Now, this next problem, just like the one we just did, different values. I want you to pause the video, set this up, and then work through it to make sure that you can understand how to get the right answer. So I've set it up so that I took my radius times my angle theta, from my smaller gear, turn that into radians, equal to S, which is radius times theta. This is my unknown. I'm going to have to finish solving by dividing whatever I get here by that radius 4.8, and that's going to give me my angle in radians. So I've got 2.5 times 225 pi divided by 180, and then I'm going to divide that by 4.8. That's my value of my angle in radians. I'm not going to round that off. I'm going to take my angle theta in radians, about 2.045, and I'm going to turn it back into degrees. I need to multiply back in degrees to get a value for theta in degrees, because that is my answer to my problem. So I'm going to leave that without rounding it off, times 180 divided by pi. And I get 117.1875. So 117.1875 degrees, significant digits. I've got 2 significant digits for each of my measurements here. So I'm not going to keep more than 2 significant digits. Well, to round this to 2 significant digits, that's going to round to 120 degrees. Don't forget to watch out for significant digits, or in my math lab, pay attention to where it tells you to round. Okay, one last page in this section, and we're going to talk about finding area. Area of a sector of a circle. A sector of a circle. Their blanks confuse me sometimes. The area of a sector of a circle, that is the portion of the interior of a circle intercepted by a central angle. So when I have a circle, and I'm like our latitude problem where we looked at the differences between the 2 latitudes, this pie shape is a sector of a circle. That is a sector of a circle. The area of a sector of a circle is defined by this formula, as long as you're using theta in radians. And once again, there's a warning that when you're working with this equation, theta must be in radians, or it's not going to work correctly. You're not going to get the right answer. If you work with a value for theta given in degrees, you will not get the right answer to your problem. Okay, application problems. We've got a sector-shaped field, and we want to know the area of this sector-shaped field. So it's a pie shape, and I probably did not just draw it very well. So let's draw again. It's a central angle of 108. Well, 90 is a right angle, so let's make it bigger than 90. This is going to be the sector of my field, where this central angle is 108 degrees. And I want the area of all this. I want to know how much area that covers. The radius is 15.2, and notice it's given to me as 15.20 feet, 108.0 degrees, so I'm interested in keeping 4 significant digits in my answer. My area formula, 1/2 r squared theta, as long as theta is in radians. So 1/2 r squared, here's r, 15.2 squared, times 1/2 is just this 15.2 squared divided by 2. And then theta is given in degrees, so I know I'm going to have a ratio here, because I have to change my degrees, have to divide out that 180 degrees, multiply in pi to get it into radians. When I do this, I'm left with area. Area is measured in units squared. When I plug this into my calculator, I should come up with, to 4 significant digits, 217.8 square feet. Your units are important. Make sure you're answering with your units, and that when you answer for area, it's units squared. Yeah, that was just my mistake. Alright, one last example. Center pivot irrigation system provides water to a sector-shaped field. Center pivot irrigation system. So you've got a sprinkler set here, and it's going to pivot through an arc. This particular center pivot irrigation system provides water to, has a radius of 321 meters. So 321 meters is the radius, and has a pivot angle of 15 degrees. So this is the area that it's going to water without being moved. We've got our pivot angle here of 15 degrees. Find the area of the field that's going to get watered without moving your sprinkler. So S equals R theta is not the right formula. A equals 1/2 R squared theta as long as theta is in radians. So we've got 1/2 of R squared times theta. Theta is given in degrees, so I gotta fix that. I've got to use my conversion factor to convert it to radians. This is what my equation is going to look like. Or I could rewrite this as 321 squared over 2 times this ratio. How many significant digits am I keeping? Well, I'm going to keep according to the measurement typically. So we're going to choose to keep 3 significant digits. This one's a little weird because my pivot angle is only 15. It really should be 15.1 degrees. If I'm keeping 3, when I round to 2 significant digits, that definitely changes my answer. Now let's look at why. This is why you need to pay attention on my math lab to what it tells you to keep. So if I plug this all into my calculator, if I say, all right, I've got 321 squared, and I'm going to divide that by 2, and then I'm going to multiply that by 15 pi and divide it by 180. This is the square meters that I have that's going to be watered. So I've got 13,488 and a little bit more meters squared. That's 5 significant digits if I round it right there to the nearest whole square meter. If I go to 3 significant digits, that's about 13,500 square meters. If I go to, that's if I do 3 significant digits. If I went to 2 significant digits, well, 2 significant digits I would have to round down, and that would be about 13,000 square meters. And I lose a lot right there, right? That's not very close. This is rounding up a little bit, yes, but this is just not very close. I've cut off almost 500 square meters from the amount of area that's being watered. So significant digits get tricky. Figuring out the best place to round can be a little tricky. My advice to you is always read those blue words in my math lab by your answer box that tells you where to round. You can also sometimes click through and do the show me an example or how to solve this, and click through to the end to see what their answer looks like, to see how they chose to round.